Today I will talk about the CO molecule. So what is CO? CO is carbon monoxide, and it has this kind of Lewis dot structure. I will talk about the ligand properties of the CO molecule, and it has two properties actually. One of them is π-accepting. The other property is the sigma donation property. So π-accepting properties is also called as back donation. I will use this word next part of this lecture. And then I will also mention the trans effect. I will explain this concept by giving some examples. But before understanding the CO molecule, we have to draw the molecular orbital diagram of CO molecule. So it is very important to understand. So first we have an energy diagram. We have a 2p orbitals of the carbon, and we have a 2s orbitals of the carbon atom here. And we have also oxygen. Oxygen 2s is little bit lower. Why? The reason is that oxygen is more electronegative than the carbon atom. I hope you know that. And 2p orbitals of the oxygen is between the 2p and 2s molecular of the carbon atom. So it is something like between. And this is the 2p orbitals of the oxygen atom. Okay. And we know that carbon has 6 electrons. So there are 4 valence electrons for the 2s and 2p orbitals, and oxygen has 8 electrons. So it has 6 valence electrons. So I want to put the electrons here. 1, 2, 3, 4, 5, 6. So actually I put in a wrong way, since these orbitals are degenerate, right? And we have 4 electrons in the 2p. And we have 4 electrons in the 2s orbital. And then we can start to create our molecular orbitals for the CO molecule. So we have sigma and sigma stars. So I will call this molecular orbital as sigma, and this is the sigma star orbital. 2, this is the second orbital. I will write 2, and both of them is completely occupied, of course. And we have pi orbitals, so we can call it these are the first pi orbitals. They are completely degenerate. They are in the same state. By the way, what does it mean, degenerate? It means that they are same energy level. So we will use this term so many times. So I want to mention here, we have sigma, 3 sigma, star molecular orbital. We have the anti-bonding orbitals and sigma anti-bonding orbitals. So I don't want to put all the dots actually. It makes it very crowded. But okay. And I will put the electrons here. So we have totally 10 valence electrons. And if you count in the MO diagram, you will see that we have 10 valence electrons. I will clean this part, since I need more space here. So we have a LUMO orbitals, lowest unoccupied molecular orbital. LUMO is important, and we have two of them, two degenerate LUMO orbitals. And we have HOMO orbitals, which is the highest occupied molecular orbital. And the important thing is that actually this HOMO orbital is slightly anti-bonding character. What does it mean? So if you remove the HOMO orbitals, the molecule become more stable since bond order increases, or the CO bond strength increases. And we can understand it actually if you look at the CO and CO plus bond length. We realize that CO bond length is bigger than the CO plus bond length. So it shows that automatically these HOMO orbitals are actually anti-bonding. Why? Since in CO plus we have non-valence electrons, and in this case we remove one of the electrons here, and it increases the bond order, and when bond order increases, CO bond length automatically decreases. So these are the experimental proof of the anti-bonding character of the HOMO orbital of the CO molecule. So this is important. But in our case, of course, there is one electron here. So you know that this is the bond length. This thing can stay here. But I want to write the important points in here. This lecture will probably longer than the others, but this is probably the most important lecture, by the way. And HOMO, highest occupied molecular density, firstly molecular orbital, electron density is more on the carbon atom. Therefore, CO molecule binds from the carbon side to the metal centers, since the electrons are more on the carbon side. And as I mentioned earlier, we have two important properties. One of them, CO is π-accepting. What does it mean, π-accepting? Π-accepting means that if it takes the electrons, the 2 pi star orbitals will start to fill. Okay, this is the π-accepting ability of the CO molecule, and it is possible. But if it accepts the electron or the electrons, it can accept more electrons, then the bond order of the CO molecule decreases. This is important. And also, HOMO orbitals are slightly anti-bonding. So, and the CO molecule is sigma donor ligand. What does it mean is that, so there's no electrons here. So it is a sigma donor. If it is a sigma donor, then it will use these electrons, right? It will use these electrons, and these electrons will go to the metal center if the CO behaves like a sigma donor ligand. And if it is a sigma donor, then the bond order will increases. How can we observe the bond order change? We simply look at the CO stretches in the infrared spectroscopy. And if the infrared spectroscopy, if we saw an increase in the CO stretches, we can understand that the CO bond order increases so that it becomes a sigma donor ligand. If it's the opposite the case, so if the CO stretches on the infrared spectroscopy decreases, then it is a π-accepting group since the bond order of the CO decreasing. And I want to give some examples, but before giving them, I want to draw the molecular orbital interactions or the interaction of the CO molecule. As I mentioned, we have a LUMO orbitals and we have HOMO orbitals, right? And you should able to draw them. We have a pi star orbital, we have a carbon center, and we have an oxygen center, and making it bigger to show it more clearly. And this is the 2 pi star. So this is the LUMO orbital. I am drawing this orbitals. So we have a bond between the carbon and CO, and carbon side orbitals is bigger than the oxygen side, and we have of course a face for the orbitals. So this is the pi star orbitals of the CO, and maybe I should make it a little bit smaller. Okay, this is the pi star orbitals. You can also draw it, it is important. And we have HOMO orbitals. By the way, this is the one of them. The other is coming towards us. So it seems something like this, right? So again, there's a face. So for instance, if this is the Z direction, and this is the X direction, and this is the Y direction for this one, and here, for instance, and this is the on the plane. This is on the plane. Or it is on the how can I say, this is on the XY plane. Yes, this is on the XY plane. But you understood, since we have two degenerate LUMO orbitals. So we have two of them, but we can only use one of them to show the event. Okay. And we have HOMO orbitals. And the HOMO orbital of CO is again slightly anti-bonding orbital, and again I want to draw it. We have a carbon, we have oxygen, we have a one phase here, and we have two phases here, and there is a note, of course. This orbital, molecular orbital, is completely filled. And what is the interaction between the metal center and CO molecule? So there might be two different interactions. In the first case, I want to talk about the pi accepting ability of CO. Oops. I will put it here, and I will draw the metal orbitals. Okay, this is the one of the T2G orbital. This is T2G metal orbital. So it comes from the symmetry, as you know. We have a carbon center, we have oxygen center. Okay. I am drawing the same orbitals. Actually, I am drawing the same thing here. 1 second. So these two things will interact to each other. This is the metal, and this is the carbon monoxide. And we have of course, same phases. Therefore, there is a bonding interaction. But what is happening is that CO is accepting the pi electrons. So therefore, CO takes the electron from the metal center and this is also called as back donation. And T2G orbitals of the metal, so this is the metal, gives electron to the pi star CO molecule. So maybe we can write 2 pi star. But you understood, I guess. And the other case is that we have a, so I am talking about the sigma donation. Sigma donation ability of CO. We have again similar thing, but in this case we are using the different molecular orbitals. So we have a metal, and for instance we can use the dz square. Right, this is if this is the dz square orbital, it has this kind of face. This is the dz square, but also the x square minus y square orbital can interact. Therefore, I will call these orbitals as EG orbitals. And EG orbitals can interact with the CO molecule. And in this case, CO gives the electron to the metal center and creates the bond between the metal and the carbon. And how can we observe this event? How can we observe the interaction? This is the main question. So, as I said previously, bond order changes. So, if the CO molecule accepts the electron, electrons will come to the LUMO. Right? Electron will come to the LUMO here. And the bond order will decrease. If the bond order decreases, then the CO stretches in the infrared spectroscopy also decreases. And the vice versa is true. So this is the pi accepting case. So this is pi accepting case, or the CO back donation case. It is the same thing. And in the sigma donation case, there is also sigma donation case. So in this case, CO HOMO anti-bonding orbitals goes to the metal center. In this case, bond order increases, which is the completely opposite of the pi acceptance. And when bond order increases, CO stretches also increases. But what is the CO stretches? So CO is a infrared active molecule, of course, and in gas phase, CO stretches is 2143 centimeter minus 1, and centimeter minus 1 is wave number. If you don't know, we use the wave number in the infrared spectroscopy. And we will look at the CO stretches. I want to give example, and I will write some complexes: vanadium complex, chromium complex, manganese complex, and one iron complex. So if you look at the periodic table, so vanadium is D5 system, chromium D6 system, manganese D7 system, and the iron is D8 system. And the CO stretches for these molecules, so we are looking at the carbon oxygen bonds here, okay? So it decreases for the vanadium case, so it is 1976 centimeter minus 1. It is 2000 for the chromium complex, it is 2013 for the manganese, and it is 2023 centimeter minus 1 for the iron case. So what we know here? So firstly, for all cases, you're taking electron from the metal center. So if you're taking, CO is taking electrons from the metal center, but not equally. So it is taking more electron for the vanadium case, right? Since the CO stretches decreases more. And the pi-accepting ability of CO is better for the vanadium case. So it means that in vanadium case, or for the vanadium CO6 complex, pi-accepting ability is better, is the best actually. It is the best among them, among all the complexes here, is the best among these complexes. These are the complexes, and pi-accepting ability of CO in this complex is very good. But why this is happening? So, for instance, iron is more electron rich, but it can give less electron than the vanadium, and vanadium is D5 system. The reason is the orbital interactions. So orbital interaction in this case is more important than the electron richness of the metal centers. And the orbital interactions are worse between the iron and the carbon case. And you can keep it in mind. I will not write it. And another example. So we have a silver CO plus, and we have nickel CO4, we have cobalt CO4, we have iron CO4 2 minus. And again we will look at the VCO, CO stretches. So for the silver it is 2204 centimeter minus 1, and as you remember, VCO was 2143 centimeter minus 1, and it increased. So it definitely increased, right? And for nickel complex it is 2060. For the cobalt it is 1890, and for the iron it is 1790 centimeter minus 1. So there is a back donation here, of course, or the pi accepting ability. Or it is the same thing, CO back donation. So CO gives the CO takes the electron from the metal center, and pi star of the orbitals of the CO molecule fills. It decreases the bond order. When bond order decreases, VCO stretches start to decrease. So this is the case here for the green samples. But the silver case is different. And what is happening is that sigma donation ability of CO dominates the pi accepting ability in silver complex. So 3 sigma star orbitals of the CO molecule goes to the silver side, or the silver center, e.g. orbitals, definitely. And this is the HOMO orbitals, as you remember, slight anti-bonding HOMO orbitals of the CO. and anti-bonding. When anti-bonding orbitals is going to the, if it goes to the silver center, then the bond order of the CO, increases, and increasing bond order increases the CO stretches for this sample. So why we are using the infrared spectroscopy to look the CO stretches? So we have other techniques, right? So firstly, by looking at the CO stretches, you can have an idea about the charge of the metal. So we can learn the charge on the metal. So we cannot directly learn, but we can predict. At least we can predict. So this is important. And infrared spectroscopy is a good characterization tool for the complexes. And it is also fast and useful tool, as you see. We can compare it with the VCO stretch, free stretch of the carbon monoxide. And in inorganic chemistry, of course, XRD is very useful, but it is used for the crystal structures, crystal morphologies, but it doesn't give any information about the oxidation state. So it doesn't provide any information about the oxidation state, so it is not very useful. Therefore, infrared spectroscopy is the key method in this case. And I want to give another example. So I will write a reaction. We have a molybdenum. Complex, and this has definitely octahedral structure, right? Or octahedral symmetry. We have CO molecules, and we will use a PPH3 ligand. So it is by the way, PPH3 is a good sigma donor ligand and makes the electron sensors rich. So it binds to the metal centers, it donates the electrons, and the metal center of the complex become more electron rich. And if we react the complex, we will add one PPH3, and we have a CO molecules here, okay? And if we add them one more, we can also add more phospholigand, and we can produce a cis isomer. So this is definitely cis, right? I will make them smaller. And we can continue to the reaction. And if we try to continue, we can add one more phospholigands. So for instance here. Okay. But if you try to add more, guess what? There is no reaction. But why? What's happening? Why we can't add the fourth one? No addition of the fourth phospholigands. Okay. So you can think the steric effect. like, right? So yes, so you can think steric effect, whether it is the case or not. But if it was the steric effect, then why there's a cis formation, right? So instead of the cis, we can have a trans product. It is not the case, so we have a cis here. So the steric effect is not the answer. Steric effect does not explain situation here. And you can think electronic effect. But molybdenum oxidation state will not change or does not change. Why? Since the phosphoryl ligand is neutral and it is also 2 electron donor, and the CO ligand is also neutral and it is also 2 electron donor ligand. Therefore, there is no oxidation state change on the metal center. But what is going on here? And I want to number them. For instance, if this is the fourth one, this is the third product, this is the second product, and this is just the beginning. So from going to 1 to 4, number of phenyl groups increases, right? If you go from the 1 to 4, phenyl groups increases. And when the phenyl groups increases, or the phosphoryl ligands, of course, phosphoryl ligands have the phenyl groups, it donates more electron to the metal center. We have electrons on the ligand, we have a metal center, it donates all the electrons to the metal center. And when it donates the electrons, there is something happening. That is the back donation on the CO molecule. And back donation for CO increases in each ppH3 substitution, since electron density on the molybdenum increases due to this phosphoryl ligands. And pi back donation is happening. So we have a metal center and pi back donation happens to the carbon side. So electrons goes to the pi star of the CO when the ppH are added more. And when this is the case, of course, CO and metal bond strength start to increase in each phosphoryl ligand substitution. And when carbon and metal bond strength increases, you cannot remove the CO molecules from the complex, therefore you cannot substitute more. And there is also another event which is called as the trans effect. This is the other important thing. So CO molecules interact with the, for instance, the exert orbitals of the molybdenum, right? For instance, we have a one molybdenum here. This feeds the electron due to the phosphoryl ligands more, so electron density on these orbitals increases, and the CO pi star orbitals interacts with the d orbitals of the molybdenum. And we have another carbon here. So if another carbon gets close to the metal, I couldn't draw the last one, I guess. there is a competition between the same d orbitals among the CO molecules. So there is a competition between CO molecules for same d orbital. Therefore, substituting more carbon monoxide is also hard. But also, there is another event. Molybdenum also interacts with the phosphonoligands. However, metal centers use different molecular orbital to interact with the phosphonoligands. For instance, we have a molybdenum center. We have a d exert orbitals. These are the d exert orbitals. For instance, this is the x-axis. Then this is the z-axis, and this is the x-axis. And we have a one phosphonoligand here, for instance. We have a lone pair of the phosphonoligand also. So it has 2 electrons. And these electrons will directly interact with the dz square of the, so this is the dz square of the metal center, and it will interact this orbital. So there is no competition between the ppH3 and the CO. However, there is a competition between the CO molecules. So, and there might be also other competition between the ppH3, since another ppH3 can try to come here in the solution, and there might be a competition between the phosphonoligands also. But the important point is that why we can't substitute more, since the carbon metal bond becomes stronger in each substitution, in each phosphonoligand substitution. So this is the answer of this problem, but I wanted to show also transit effect on the substitution. So I want to summarize the events, since this is important. This is the probably most important course part of this lecture series. So we showed the MO diagram of the CO, and it is important to understand the π-accepting ability or backbonding of the CO molecules. And we also showed the sigma donor ability of the CO molecule, and we showed the effect on the bond order. And there is a electron transfer from the 3 sigma star HOMO orbitals to the metal Eg orbitals. And in π-accepting case, this is the opposite. T2G orbitals gives the electron to the 2 pi star orbitals of the CO molecule. So they are different from each other. And HOMO and LUMO orbitals of CO have anti-bonding character. Both of them, HOMO and LUMO of CO molecule, have anti-bonding character. This is the other important problem. And in the last example, you saw that backbonding makes the carbon metal bond stronger, but makes the CO bond weaker. So backbonding makes the carbon oxygen bond weaker. I think this is the other important information. and we observe them in the infrared spectroscopy. Infrared spectroscopy shows stretches. Stretches gives information about the bond order, and we can predict what is happening in the molecules. So in this video you saw that infrared spectroscopy is very useful technique for the organometallic compounds. And if you have questions, you can ask in the comment section. You can make comment, and if there's a mistake you can also mention that. I will try to fix it. And thank you.